I have a couple examples for us to work through together that'll illustrate how we can now solve these problems using inverse trig functions. So the first one right here, you'll notice that the usual u substitution where we would do 4 minus x squared is u doesn't work because there's no x up here. So we don't have a form of du on the numerator. So we're not going to be able to just do a straight up u substitution. Instead, we're going to try to make it look like the derivative of arc sine. And because it can look like the derivative of arc sine, we'll be able to integrate, make it look like that. But we have to change how this whole expressions look in order to do a u substitution to truly see arc sine. So remember, the derivative of arc sine is 1 over the square root of 1 minus x squared. And here we don't have a 1 minus x squared, we have a 4 minus x squared. So we're going to have to change this into a 1. In order to change this into a 1, we're going to need to divide this by 1, which means divide this by 4, which means divide this by 4. And in order to do that, we're going to have to multiply everything by 4 as well and factor that out. So here's how we're going to do it. We're going to pretend that we're multiplying outside of the square root by 2 over 2. The reason why we choose 2 is that when we pass this inside the square root, the 2 becomes a 4. And we only want to bring the denominator inside, so that'll change this 2 here into a 4, but this 2 here will stay intact. So let's just do that step. So we get the integral of 2 over twice the square root of 4 minus x squared over 4. The only thing that I passed inside, the only thing that I changed is this 2 that is outside here. I brought it inside, and now it divides the whole inside of the radical. So again, when you take a number outside a radical, pass it inside, it gets squared. Okay, because if we took the square root of 4, we would get 2 out here. So now that we've done this first step, we're in good shape because the 4 divides 4 becomes 1, and the 4 dividing x squared becomes x over 2 being squared. On the outside, notice that my 2 and my 2 here are going to cancel, and I'll be down to 1. It's really important every time you write derivative to make sure you start with the integral sign and you always end with a dx. I've seen a number of you drop the dx in your postings online. You can't do that. You always have to write the dx. It's incorrect, and you will lose points if you don't. So let's go ahead and give it one more layer of simplification. The 1's cancel. Sorry, the 2's cancel, become 1. So I have 1 over the square root of. And here my 4 over 4 becomes 1. And here I have x squared over 4 dx. Now, I could just let x squared over 4 be my u, because actually I don't want that to be my u, because I want my u to be squared, right? So what must u be in order that when you square it, you get x squared over 4? Well, it means that this 4 needs to be squared as well. So I'm going to actually include it with x in what's being squared, and that 4 is going to become a 2. So once more, we're going to rewrite this now as the integral of 1 over the square root of 1 minus x over 2 being squared itself, dx. And now you see that when I apply the square to numerator and denominator, I do get x squared over 4. So now I'm ready to do my u substitution. I'm going to let u be that thing which is being squared, which is x over 2. So du is going to be dx over 2. And now I can replace dx by 2 du. And so my last form, I'm going to get the integral of 1 over the square root of 1 minus u squared times I get 2 du. So my 1 becomes a 2 du. And this integrates exactly to twice the arc sine of u plus c. And now we back substitute instead of u, we're going to have x over 2. I'll just give myself a little bit more room right here. And so I'm going to get twice the arc sine of x over 2 plus c. So that's a complete solution. The steps, again, is to try to make the form given to you look like the result you know, which is going to be a 1 over square root of 1 minus u squared. The 2 here doesn't really matter because, in effect, I'm pulling it outside as a coefficient. That's why the 2 comes out here, and I just treat this as if it were a 1. I hope that explains all of the pieces here and you're not confused. Maybe I need to move this a little bit more so that you see me the whole time. There we go, much better. Let's go ahead and work on the second one as well, because this is more like what I showed you last week. Because we have an expression on the numerator that isn't exactly the derivative of my denominator, I can't do my first step as u is 9 plus x squared. Yeah, the derivative is 2x, so I'd be able to deal with this, but I'd still have a 1, and that 1 would be a problem. So my first step here is I have to split this into 2 separate integrals. So this will be x over 9 plus x squared plus 1 over 9 plus x squared dx. So I'm just splitting my numerator into 2 pieces, and I'm going to do each integration separately. So we'll do this one by u substitution, because that's going to work. And this one, I'm going to try to set up an arctan. So for the first one, x over 9 plus x squared dx. And then the second one, integral of 1 over 9 plus x squared dx. So my u substitution here is u is going to be 9 plus x squared. Du will be 2x dx, which means that x dx is going to equal to du over 2. Notice that I solve for x dx because that's what I see on the numerator. So I'm just going to divide both by 2 to get rid of that piece. So now I'll know that I can replace my x dx by du over 2. And I'm ready to solve this first piece, which just will be the integral of du over 2. And here I'm going to have 1 over 2 u, and that'll be du. So the substitution is going to go pretty much like we want. The piece we're going to have to worry about, though, is this one here, because this doesn't exactly match the derivative of arctan. The derivative of arctan is 1 over 1 plus x squared, and here I have a 9. So I have to do the same trick that I did here. I'm going to have to bring this 9 underneath the x inside the square in order to change this into a 1. So I'm going to start by multiplying and dividing everything by 9, right? So in essence, what I'm doing is I'm factoring this 9 here on the denominator. So 9, I pull it out. And here I'm going to be left with 1 plus x squared over 9 dx. All right, let me erase the rest of the board so we can keep working. All right, the first piece, du over 2u becomes natural log. So I can pull out the 1/2 in front. 1/2 the natural log of u plus. Here, I'm going to pull out the 1/9. And then I'm going to integrate 1 over 1 plus x over 3 squared. So because I have x squared over 9, 9 is 3 squared, I can combine the x over 3 and square the whole thing. Dx. Now I can substitute back, right? My u was 9 plus x squared. So I get 1/2 of the natural log of 9 plus x squared. I don't need absolute values here because x squared is positive. So my inside is already positive. So we are safe. Over here, I'm going to do a u substitution on x over 3. And so du will be dx over 3. So dx I will replace by 3 du. So I'll have 1/9 times the integral of 3 du over 1 plus u squared. And now this 3 I can pull out front as well. And I'm just integrating 1 over 1 plus u squared, which is the arctan of u. So I get 1/2 of the natural log of 9 plus x squared plus 3/9 of the arctan of u plus c. And since u is x over 3, I do my last back substitution. The 3 over 9 becomes 1/3. And so I'm left with 1/2 of the natural log of 9 plus x squared plus 1/3 of the arctan of x over 3 plus c. And so this gives you your typical problems involving inverse trig functions. We set them up by seeing these fractions as really hidden ways of seeing the derivative of the inverse trig functions. And so we can go back. Notice that we never need to use the arc cosine because the arc cosine is just a negative function for the arc sine. So arc sine, arctan, they're the only inverse trig functions that you're going to need for these trigs. Please post questions in the discussion board, and I'll see you in the next video.